My name is Gideon Mendels. I'm the CEO of Comet.ml, as Simon mentioned. We like to say that we do for machine learning what GitHub did for code. We allow machine learning teams to automatically track their data sets, code, experiments, and models. Before Comet, I actually started my career as a software engineer, but I've been focused on machine learning and deep learning for the past 5 years. I was a grad student just a few buildings away from here at Columbia, where I was working on speech recognition, specifically building speech recognition models on low resource languages where we have little data, and deception detection, which is essentially building a lie detector using machine learning, both on acoustic and lexical signals. After that, I spent some time at Google where I did deep learning research on hate speech detection. I'll actually spend more time on this in the talk because I think there's really interesting learning from that time. And in my previous company, we built an app called GroupWise, which is a chat analytics app where users send their chat history from WhatsApp, Viber, Line, and get a bunch of entertaining metrics, like who talks about sports, politics, who are the funniest, and so on. And we got to deploy about 50 machine learning models in production. And for those 50 that went to production, there are probably 5,000 that didn't. And in today's talk, I'm going to focus on running effective machine learning teams, common issues, challenges, and solutions. I'll focus more on the workflow and the tooling because that's where we believe the problems are. So the agenda for today's talk, just very hard to see here. I'll cover some of the advances we've seen in deep learning recently, and I'll share a case study from my teams at Google working in hate speech detection. And then I'll address the main problems as we see them around visibility, reproducibility, and collaboration. I'll just try to resize the screen here. All right, perfect. So everyone's talking about the deep learning revolution, and we've seen some significant improvements in the academic world, but sometimes it's hard to distinguish what's real hype and what's actual improvements. And indeed, a lot of businesses are challenged and having a hard time extracting business value from their models. I'll try to walk you through the advances we've seen in recent years to try to give you an idea of how impactful deep learning was or is. So the first example is ImageNet. For those of you who are familiar or not familiar with it, ImageNet is a data set of about 18 million images from anything from common objects to breeds of dogs. It has 1,000 classes. So the underlying task here is given an image, try to detect which class it belongs to. And ImageNet is a very popular benchmark for computer vision models. Up until 2011, we mostly seen traditional computer vision methods solving this problem. But then in 2012, something interesting happened. A model or a network called AlexNet was submitted and managed to improve previous year results by 10%. And this is an absolute improvement. And what's really interesting is the technique or the algorithm, so specifically here convolutional neural networks with max pooling, wasn't something that was new. We've known it for about 15 years before that. What was interesting is AlexNet was implemented in CUDA, which is a programming language used to program NVIDIA GPUs, which allowed them to train the network in about 6 days. So in a course of about a year, they had time to improve the network and try different experiments, different hyperparameters, until they got this amazing result. And over the next years after, we've kept seeing improvements up until in 2015, Microsoft released ResNet and actually managed to beat the human performance on this task. And since then, we've seen more and more improvements. The second data set or problem that I want to talk about is from a completely different domain of speech recognition. So this is the switchboard data set. It has about 260 hours of speech from about 540 different speakers. And the underlying task here is speech recognition. So given a speech utterance, try to predict the sequence of words. And during the mid-2000s, we were kind of stuck. Word error rates were not really going down and pretty much leveled out. And then again, in 2012, pretty much the same time AlexNet came out, the first implementation of DNNs was successfully implemented. So speech recognition traditionally has two pieces, an acoustic model and a language model. In this case, they were replacing the acoustic model with the DNN and managed to improve the result with about 3%. So it's not the 10% we've seen in AlexNet, but still pretty impressive. And then in the next years, the improvement continued and continued. We started replacing the language models from HMMs to LSTMs, and then we've seen systems that are completely end-to-end, up until Microsoft, again, in 2016, managed to reach human parity. And at this point, you might be asking yourself, well, I've been using Siri and Alexa. It's kind of hard to say they reached human parity, and I definitely agree. I think this serves as a benchmark or academic benchmark to try to understand the improvements, but we have a long way to go till we actually deploy these and these word error rates in production. So for companies like Google and other companies that have the resources to train those models, the knowledge to train the models, and the data, they're actually doing a really good job extracting business value of this. So what this chart shows you is the number of directories that contain model description files in the Google code repository. And you can see this is growing exponentially. And while this chart ends in around 2016, I'm pretty confident that that growth continued. And what's interesting is we're not really seeing it on typical academic tasks. Yeah, there's speech recognition here and computer vision, but we're also seeing Google Maps, drug discovery, Android, and so on. So it really spans the entire product area. So we live in this machine learning pioneering age, and it's really exciting to be part of this. And yet, while this academic research has been super impressive and super successful, the biggest obstacles are really around our processes and tools. So we think the biggest problems are in visibility, reproducibility, and collaboration. And I'll talk more into depth about them later down this talk. But before that, I'd like to share a quick case study. So this is from my time working on hate speech detection at Google. I'll go a little bit more into details on the science side, the data engineering, and the algorithmic side of things. Hopefully they'll give you some background before we talk more about the problems. So the goal here is detecting hate speech on YouTube comments. Unfortunately, if you ever used YouTube, you probably know there's quite a lot of it, so this was very important for us. The underlying scientific task is essentially document classification. So given a YouTube comment, which is a sequence of words, try to detect whether it contained hate speech or not. So it's just true or false. And at the time, our data set was pretty limited, so we only had a few thousand examples. And we already had a model in production when we started working on this. And the goal of the project was to try to outperform this and gain better results. So, excuse me. So if you want to outperform the production model, a good place to start is what's running in production, right? And to our surprise, it wasn't that easy to answer that question. So in order to answer this question, you need a few things. The first thing is code. So fortunately, in this case, we had the training code. It was checked in version control. That wasn't a problem. After that, you need your training data. And yes, we had the training data, but we had about 10 different versions of it. And we weren't sure which one was one used to train the production model. So people tried normalizations, cleanup, and so on, and it was just sitting in a file system, and we weren't sure which one was used. After that, you need the hyperparameters. So those of you who are not familiar, those are all the knobs we turn to try to get better results from our neural network, anything from the number of layers, the number of neurons, learning rate, and so on and so on. In our case, originally, the hyperparameters were fed as command line arguments when the script was originally executed, and they were just completely lost. Once you train a model, you get two things on the other end. One is your model binaries or your weights, and we had that because that was running in production. That wasn't the problem. And the second thing is the results. So we managed to find the result. It was in an email sent to the team. But we only had accuracy, so we didn't know precision, recall, or other data points that might be useful for us. So as you can, hopefully this starts to give you an idea of how challenging this is. Now, we managed to rebuild this training pipeline based on those pieces we collected and retrain the production model again. And indeed, we got, oh, sorry. Before that, let's dive a little bit more into the details. I assume this is a more technical crowd, so I don't usually cover this, but it might be interesting for you guys. So what was actually running in production? We use a combination of two techniques, paragraph vectors and an SVM. So paragraph vectors is unsupervised algorithm that allows you to generate a feature vector from text. if you're familiar with Word2Vec or word embedding, it's the natural extension from the word level to the document level. And the underlying assumption there, or the idea was, even though we only had a few thousand examples that were labeled, we can train this thing in the entire YouTube comments corpus and hopefully get a better result. And once we had that paragraph vector model trained, we can generate features for later training for our label dataset and feed it to an SVM. SVMs are kind of known to perform pretty well on small datasets, so overall this made sense. So we built this entire thing, we retrained it, and we actually did get the same result we saw in the email. So 95% accuracy. If you're worried, the data was balanced, so the random selection here is 50-50. So we're doing pretty well here. Now, once we had that in place, we figured, okay, what's the next step and how can we do better? Now, commonly when we work on those kind of problems, you try and establish some kind of baseline. So usually a baseline is a pretty simple model, something that's cheap to train, usually has easier to understand it, and so it has some explainability built to it, and it gives you some idea of how hard this task is, right? So what we use, and if you ever worked on NLP or document classification, this technique shouldn't surprise you. We used n-grams, which is a way of, again, generating feature from text. So n-grams, just quickly, if n equals 1, so we're talking about unigrams, you basically replace the word with an ID from the vocabulary. If n equals 2, you replace pairs of words and so on and so on. And at the end of the day, you get a feature vector that you can feed into your classifier. Additionally, we spent a little bit more time on this and added some more feature extraction methods. So stemming, which is a way to reduce your feature dimensions. So basically, you can map multiple words to the same ID. So in this case, processing and process will map to the same word because they have the same stem. Additionally, we added stop words removal, which is usually the most common words in the vocabulary in the language. So things like with, are, at, and so on, they provide very little value to the classifier. And finally, we added TF-IDF, which is a way to normalize between long comments and short comments. So again, these are things that are pretty simple. Usually, I think they teach them in like NLP 101. So a typical baseline model in this case. So we trained this thing, and at some point, we actually started doing something that's pretty interesting. We're beating the production model with our n-gram baseline model, right? So here we have a pretty fancy deep learning technique that's getting crushed by logistic regression. A linear model has been around from like the 70s. And we did try, or someone did try baselining this task before, but they probably haven't spent as much time as we did and trying to just optimize it. So just something to consider when you try deploying deep learning networks. It might be worth it to try simpler models before that. But nonetheless, we are encouraged that we can get a better result here. So we figured, what can we do next? Is there anything else we can try? And in this case, we went to the scientific literature. We did a literature review. And at the time, there was a paper on one of the actually first successful papers on using CNN, so pretty much the same thing that AlexNet was using, but for text classification. And this was a paper by Yan-Li Kuhn, one of the fathers of deep learning, who up until recently led the Facebook AI Research Institute. And what was really compelling for us is, as you can see here, they actually tried n-grams and well. It got a pretty good result, but they managed to beat it with cognates. So we figured this looks interesting. We should probably try it as well. So we implemented our own CNN. That was pre-Keras era. We had to write the whole thing from scratch. And we trained in our data set, and we're kind of disappointed. So we're still beating the production model, but we're behind our n-grams baseline model, right? And at this point, we're asking ourselves, okay, what's going on? What could be the reason? And we figured it might be two things here. One is we have a bug in our CNN implementations. If you ever try to implement one, you know there's a lot of room for error. And deep learning networks are notoriously hard to debug. So it's not like you can run a unit test and just, okay, all tests are passing, I'm fine. So bug was one option. The second option was like, well, we're looking at a different data set, right? The paper was using the Yahoo data set, some academic data set, and the underlying distribution could be different, so we might have just lucked out, and our task is a little bit different. But in order for us to figure out if we do have a bug, we figured the only way to do this was actually running it on the original data set from the paper. And in an optimal world, we would have that available, but we actually emailed the author and asked for access to their data set, and they were super kind and they shared it with us. And we got the data set, we fed it through our pipeline, we trained the model with our CNN, and out of the other side, same result as the paper got. So this 71.2% accuracy is exactly what was reported in the paper. So far so good. We probably don't have a bug, or maybe if we do, they have as well. And the second option, if you remember, was, okay, we're looking at a different data set, right? This is this Yahoo data set. We're looking at our hate speech data set. We just might as well lucked out and time to move on. But right before we wrap this project up, we figured, what happens if we take the data set from the paper and feed it into our baseline logistic regression optimized model? And as I see some of you smiling, so as you might have guessed, we actually managed to beat the CNNs in the paper with n-grams, right? So well, the CNN result in the paper is completely reproducible. It took some time to figure it out and really read through the paper and emailing the author. And we did manage to reproduce it. But the n-grams result wasn't. And it's not because they did something wrong. They probably just spent less time optimizing it, which is completely natural. But we spent months just chasing this problem and going back and forth, trying to figure out what's going on, how can we do better than this. And if we only had visibility to what was going on, both to our production models and whatever was published in the paper, things could have looked very differently. So I've said visibility, I said reproducibility. What does it actually mean? So we define visibility as the ability to access, view, and react to machine learning processes and deliverables. So things like what's running in production, what's my model's performance, do I know what hyperparameters was used, do I know what data set was used and what version was it. And another aspect of this, and sometimes it's not clear when you first look at this, is what happens when one of your colleagues or one of your data scientists quit or leave the company or leave to another team even. So they build so much intuition and understanding of the underlying problem. And when they leave, everything they know goes with them. There's just no way to keep track of that. And when you think why visibility is so hard, there's a few things. The first thing is that the pieces required are just completely decoupled and happen in different parts of the process and even across different teams, right? So you might have a business analyst pulling the data for you with some query, and then you pass it to a researcher that tries different algorithms and different hyperparameters. And then at some point, you might pass it to a software engineer that try to make it more efficient and productionize it. And then at the end of the day, you'll productionize it, and you'll have DevOps taking care of it now. The other aspect is just there's so many tools, and everyone likes using their own favorite machine learning library, their favorite cloud provider, and people feel very heated about this. And it's hard to build this visibility when all that knowledge is spread across tools and languages and cloud providers. And finally is just outdated documentation. So most teams do try to solve this problem by having like a Google Doc or a wiki and try to document their work. But the problem is, it's completely separated from the actual process. So in software engineering, we have this notion of auto-generated docs. So you have comments in the function, and you have some system that produces documentation from it. And even there's a problem with comments becoming outdated. But here, those documents or those wikis are just completely separated. So 3 months into the process, no one's maintaining them anymore, and they're pretty much useless. So once you have a better idea of what visibility is, and maybe you manage to solve it, you have to go to the next step, and that's reproducibility. And there's very heated discussion in the academic world of what's reproducibility. Some people say that our definition is replicability. So just for the sake of this discussion, I'll define reproducibility as a way of having a recipe of multiple steps, running through those steps in the same order and getting to the same result. Some people would say that you need to have different recipes that give you the same conclusion. So you can say what I'm talking about is replicability. I'm fine with that, but in machine learning, we think it's pretty much the same thing. So what's the barriers to reproducibility? Some of it connects to visibility, but there's also other challenges here. So the first thing is just changes in data, right? Someone might have updated your training data. Even if you're reading from the exact same file, someone have touched it and changed it, and then you will get different results once you finish training your model. You can have different random seeds, so the data is shuffled differently and things look different again. Inconsistent hyperparameters, so like we've seen in our use case, we didn't have the actual hyperparameters, so even though we got to a similar result, it wasn't the exact same model. Third, there's challenges in even if you have the data right and the code right and the whole thing set properly, if you're running the same model on different versions of TensorFlow, you might get different results. So that's another challenge. There's also things like inherent stochasticity in some of the neural network models, such as dropout layers, and just difference between how CPUs or different platforms of GPU run through the same instructions. So you might get some variability there. And then the last thing is collaboration. So we speak to a lot of machine learning teams, but mostly it's just a group of lone wolves sitting in the same room. And honestly, it's very hard to do it otherwise, because there's no way to share the information. There's no way to having a constructive discussion. The easiest way to collaborate today is calling someone, hey, can you look at my screen? This is what I'm seeing. So it's really hard to collaborate. And as you can imagine, if you've seen software teams, once you figure that piece out, things really start moving. So at this point, you might be asking yourself, this sounds about true, but I know this tool is called Git, and it's really great, and you should really check that out. And indeed, most companies try to solve this problem with version control or Git originally when they encounter it. So Git is an amazing tool, and it's super flexible, and there's like a million ways to do everything on Git. So I'll just walk you through one example of how you might use Git to solve this, and hopefully you'll get an understanding of why it's not the best solution. So I have a set of commands here. I don't have any more code on my slide, so that's it. But basically what I'm doing here, so I'll try. Right, so I'm checking out a new branch, and I'm naming it with some kind of an experiment name. I'm then calling my Python training script and feeding in the path to the data set, my learning rate, so those are all hyperparameters. And I'm actually really careful, so I'm saving my results into a text file. The model's finished training, and I'm adding the results to the branch, committing it, and pushing it. So far it seems like I know what the code is, I kind of know what the data is, and I might even know what the results are. But once you start doing this after a few weeks, and you go to GitHub, for example, you see something that looks like this. So on the left side, I just have a list of branches, and I have no idea what does that even mean. Even if I try to name them with more semantic meaning, it's pretty challenging. And then on the right side, so I might have multiple training scripts in the same directory, and that's pretty common use case. And I have this results, but where did it actually come from? It's really hard to answer that question. And again, you could be very careful and try to connect all those pieces, but Git was just not designed for this use case. And when you think about it, all those tools we've been building, anything from our IDEs to syntax highlighting, all those things were designed for software engineering workflows. So in a typical software engineering workflow, and I know there's a lot of variety of how different companies do this, as a software engineer, we develop something. When we feel like we're ready, we commit it. It gets built by a CI/CD system. It gets unit tested by a test we wrote and some other people wrote. And then it might reach, staging. And then by some kind of criterion, it will eventually go to production. But if you look at the machine learning pipeline, and I have a scary slide coming up, but it's really, really different. And I don't know if you can read through it, but I'll just give you the basic idea. So here on the left side, I have some data sources. Could be databases, could be my BI system. And I'm pulling data from various sources. I'm combining it, I'm cleaning it up, I'm normalizing it. And then at some point, I might try to do some augmentation or some fancier stuff on it. After that, I'll build my train, test, and validation data sets. So those are pretty critical if you want to have the right process scientifically. Here, I'm actually running the learning algorithm. So that's really the only piece that's pure code. It's getting fed by the training set, and then later evaluated by another script or the same script that feeds in the validation set. And then testing again, and finally it might reach production, but usually those models are connected to some kind of KPI, so we don't want to deploy them in GA mode right away, so we might do some A/B testing, check it against our previous model, and so on until eventually it actually reaches production. So hopefully that gives you an idea of why this process is just very, very different. So you might ask yourself, what does the ideal solution look like? And if you take one thing from today's talk is if you decide to build something internally or buy something, it has to be automated. If you're going to require yourself or other data scientists to manually tag and label and document every step of their process, you're bound to fail, because machine learning is an iterative process. It has a lot of intuition into it, and you want to actually allow data scientists to move faster and not slow them down. And we talked a little bit about tools and all those things and different infrastructure providers. So you want something that works with all of them. Because if you're forcing them to use this as the system you're using, yes, it might work for some of the cases, but very quickly you'll find people trying new architectures or new libraries, and then you'll lose the information around that. And what we found with that is once you figure out reproducibility, you're actually going to get a lot more than just that. Kind of like by definition, when you have a system of record, you can do a lot more things on top of it. So one of them is collaboration, which we covered briefly. Second thing is comparison. Comparing different machine learning models. I mean, it sounds like something that's very important to do, but it's so hard. Like if you have two branches, how do you compare them, but it's only the code, and so on and so on. The second thing is increased visibility. So not just between the team, but also for managers and execs and so on and so on. And finally, once you have a system of record of all your experiments, you can start conducting meta-analysis. So that's where it gets really exciting from a data science perspective. You can start to try and understand the problem space, the hyperparameter space. And I have one chart that hopefully will give you some idea of how that might look like. So what this chart shows you, I'll try to walk through. Right, so every axis here is a different hyperparameter. Every tick is a value of that hyperparameter, and every line here is a different experiment. The more orange the line is, so this is the range, the better the accuracy or validation accuracy is. So just by eyeballing this, just look at this area here, I can tell that if I set my kernel size to 5, I tend to outperform all my other models. So all this region in my parameter space is not, I don't need to explore it any further. And there's no way for you to be able to obtain those results and information if you don't know all those lines, so all those experiments. So at Comet, we really think that in the near future, those processes and tools will become standardized. A lot of machine learning teams look like what software teams looked like 15 years ago. And we think your adoption as a data scientist, as a manager, as an organization will really impact how well you're managing to extract value from machine learning and how well can you use machine learning as a competitive advantage. I think I'm done. Thank you so much. If you have any questions, feel free. Yeah, that's I assume. Yeah, I agree. That's a good choice for another baseline model. We might have tried that, possibly. Yeah, naive Bayes or logistic regression or SVM. In that sense, if you're trying to establish a baseline, they're all good picks.
So what tools do you use to manage all of these issues here?
Yeah, so I tried really hard not to make this a sales pitch and try to give you some value, but just so happened to be that that's what we built at Comet from all those learnings, and we try to solve that for teams and companies.
Do you factor in changes to the data itself in the workflow tracking, in addition to the hyperparameters?
Yeah, so tracking changes in data is very challenging because it could be anything from tabular data to petabytes of images, and especially things like diffing data or just keeping checkpoints and versioning. What we found out that works as a midterm solution is taking a hash of the data. So you at least know that if you're looking at two experiments and you're comparing them, that they were trained on different data set. You might not know what line change and so on, but at least you know you're comparing things that shouldn't be comparable.
Along those lines, are you simulating essentially like a model or a test case to see if the underlying model from the raw data has changed? You wouldn't necessarily know what has changed, just know something has changed. Does that make sense?
Regarding the data set?
Yeah, so like, or along those lines, like if you're getting this data, and you can see if actual data has changed, but you may not know if the underlying generator of that data has changed, right? If the model that person is, whatever he's done to create that data has changed. But if you simulate it, it's like, oh, it's like about a spike here or something like that, something abnormal or unnatural.
Exactly, yeah. So I think you're referring more to the production side of things and monitoring models. Yeah, so things like feature corruption, because you might have a data engineer somewhere else, on the other side of the building, they change something in the ETL, and then your model starts receiving the features in different ranges or something like that, and then starts basically providing false predictions. So by looking at the prediction or plotting the prediction, you might have a good idea of this model started to predict, ones much more than it used to. So it's a good way of monitoring it, yeah. All right, I think we're done. I have sorry, another question? Yeah, so Git, again, is not the best tool for this. There's something called Git LFS, large file system, that allows you to check in bigger data sets. Most of the companies we see store data sets in S3 as just as blobs, yeah.
I'm going to do a version control of data sets where you're storing that. It's like you store it in boxes.
Exactly, yeah. So that's versioning data set is super challenging to solve in a general use case. If you're just operating on tabular data, you might have some solutions out there, I think, in the open source world. But if you're using, so it really depends if you're doing vision or audio and so on.